And thank you for having me here today. It's a pleasure to be discussing this exciting new technology, which I think is going to lead to some substantial innovations in corneal refractive surgery. To introduce the session, I wanted to give a history of the development of allogeneic corneal inlays and onlays. They've been used for quite some time, but certainly advances in technology have brought them into a whole new level of utilization. This goes back now almost 3/4 of a century. The concept of remodeling the cornea was first introduced by Jose Barraquer, really the father of refractive surgery, back in 1949. He had a really groundbreaking book called Refractive Keratoplasty. And in this, he first proposed two concepts of lamellar refractive surgery: keratomileusis, which has since developed into our LASIK procedure, and keratophakia, where tissue is actually added to the cornea to change its shape. So in keratomileusis, the cornea is reshaped. In keratophakia, additional tissue is applied. Now, this was done when he started it in a very rudimentary way. Indeed, he used a contact lens cryolathe shaping instrument. It was a CO2 cooled contact lens lathe, and he needed to develop the first tools in actually harvesting the corneal tissue and then developing the lathing parameters. No one knew how this tissue would react frozen, what its hydration characteristics were, its behavior ultimately in vivo. And indeed, he first did this by hand, and finally Barraquer wrote a program for the Texas Instruments calculator. We fast forward now to 1979, where Ted Werpelen and Herb Kaufman introduced the first commercially viable corneal onlay. This was epikeratoplasty. These were lathe donor corneal lenses. So in fact, they came lyophilized within a contact lens type of container. And they were conformed to correct myopia, hyperopia, or keratoconus. They had this greenish appearance that you see on the bottom here, and we needed to rehydrate them with BSS for about an hour before utilization. It was a procedure that at the time was fairly popular. It was called the living contact lens. A trephination was made, a small groove was made under which to tuck a flange of the tissue, and then 16 interrupted sutures were placed. You see on the bottom right an keratophakia lenticle placed and the additional tissue that's now been placed onto the corneal surface. So even though this was a step better than the original Barraquer procedures, all of these procedures were plagued with a number of problems. They often had difficulty in epithelialization and epithelial ingrowth, but more frequently they would haze up, cause some scarring. They were very unpredictable with irregular astigmatism, since so many sutures were used, and the general predictability of the myopic corrections wasn't so great. So people started looking into artificial inlays. And indeed, again, it was Barraquer who first proposed an artificial corneal inlay made of plexiglass. As we know today, these kinds of things are not necessarily held well by the cornea, and this will result in melting and ulcerations over the inlay. Others introduced polysulfone grafts, which similarly had persistent epithelial defects, deposits on the inlay, and didn't work as well as one would want. And finally, hydrogels were introduced, in particular in 1981, the permalens. But even this, though it was a high water content, high oxygen transmissibility lens, led to corneal haze, inlay encapsulation, and epitheliopathy. So none of these really worked well. So again, we jump ahead to what we consider the modern inlays, and these were all for presbyopia. These include the camera from AcuFocus, which works via a pinhole effect. It's a 3.8 millimeter, 5 micron thick inlay with a 1.6 aperture, which works by the pinhole effect. The second was the raindrop from Revision Optics, which reshaped the corneal surface. It was only a 2 millimeter lens and only 30 microns thick. Early clinical studies seemed to show that it gave you good results. And finally was the Presbya micro lens, which was a refractive addition lens. It was 3 millimeters and about 15 microns in thickness. Now, none of these are really used anymore. The camera is used on occasion. Raindrop is no longer used. In fact, it was recalled by the FDA, and Presbya ended their study of the micro lens. Why is this? Synthetic inlays have biocompatibility problems. That is, even if they're quite permeable, they tend to restrict oxygen transmission to the deeper layers of the cornea, and they restrict metabolites and metabolism from the anterior surface of the cornea, leading to corneal melts, haze, and other untoward reactions. First, it was thought that if you kept them very small and very thin, this would preclude such problems. You saw how small and thin the inlays that I just showed you were. They were also placed relatively deep in order to avoid corneal melts. But despite all of these manipulations, they still cause haze, regression, inflammatory reactions. Indeed, a raindrop reported haze of 16%, which eventually caused its removal from the market. So that brings us up to corneal tissue. Corneal tissue can be a novel refractive platform because biocompatibility is not an issue. It is corneal collagen. It's repopulated with the patient's own keratocytes. There's no barrier to O2 and nutrients, so we can insert it more superficially and perhaps get more of an effect from it. And its size and thickness can be wide-ranging. So since we don't need to keep it to the thinnest possible parameters and the least diameter, we can use it as a platform for presbyopia, but also for hyperopia, myopia, and keratoconus. The viability of this was first shown to us by a variety of case studies that use SMILE lenticulae to reimplant in other eyes for treatment of hyperopia and presbyopia. Of course, the scope of these is always limited to the amount of SMILE tissue that you get from the donor eye. Sun et al. Made one of the first reports where a lenticle obtained from myopic eye was placed in a contralateral hyperopic eye under 110 micron flap. You can see on the OCT here, the cornea looks relatively clear, and you can see the steepening, which appears to be relatively stable between pre-op and 3 months. Dr. Ibrahim published a case report that used a SMILE lenticle to correct aphakia of about plus 12, and the patient, you can see here, had a fair amount of steepening afterwards. If you note the right topography, that's the difference map showing a large amount of steepening. Here's another OCT showing the configuration of the inlay. So this was a plus 10.5 spherical smile lenticle, which was placed beneath a flap of about 200 microns. So the question then is, can one use a preserved corneal tissue? Because this would certainly make procurement of tissue and preoperative preparation of the tissue a lot easier. Ganesh reported on cryopreservation of lenticles after SMILE and was able to implant 9 eyes with cryopreserved SMILE lenticles with good clarity and good results. But corneal tissue addition is becoming a more viable option nowadays. There have been great advances in eye banking, procurement, tissue processing, tissue storage. We're able to tissue shape better using femtosecond and excimer technology. And we're able to implant tissue easier and safer with more reproducible surgery using femtosecond flaps and pockets. So no longer do we need to do the more cumbersome suturing technique that we did with epikeratofakia.